Um, Tonight's topic has been published. We had reviewed the literature, looking at the current concepts, sort of a summary, what is currently evidence supported, and also looking at future application. So let's get started. Unfortunately, I don't see you. I would have asked who is familiar with TMS. Maybe just a few words. Do you see my cursor?
Yes.
Good. So TMS consists of a so-called coil. The coil has a high impulse, which generates by the electromagnetic induction theory a magnetic field, which penetrates within the skull and elicits another electric current, an electric field actually, which involves the superficial layers of the cortex. This has replaced the direct electric stimulation, and I remember a Japanese fellow who had worked with me in the United States who still had suffered electric impulses, which of course was not a good way to study cortical physiology. And about 35 years ago now, an English team, which included also the former chairman of neurology in Bern, Christian W. Hess, to develop this system. There's a number of different coils, and the coils and the size of the coils and the electric impulse define the magnetic field. Here, just to illustrate, a round coil generates a round field. This is a schematic model. In reality, this is a very short-lasting, we speak about a few hundred nanoseconds, magnetic field, which induces then an electric field. But as you can see, such a round coil has a relatively large field, while as what we call a figure of 8 coil does a very focal stimulation. Now, this is to illustrate, this was a patient participating in one of the therapeutic studies with Parkinson's disease. He chose the T-shirt. He was a very fine fellow. To show you, here we had the coil. We stimulated the motor cortex. We did offline analysis on we call motor evoked potential. So we studied several muscles. This is kind of a standard EMG recording, and we could do then off-record analysis. What you see here in the background are 4 capacitators. So the main limitation, technologically speaking, is the limitation of capacitors to maintain a high impulse in order to do high frequency stimulation. And that is currently still the limits. Now, what is the rationale in Parkinson's disease to do studies? This is, of course, a very schematic description. You have the motor circuit that connects the basal ganglia, the cortex with the thalamus, and then leads to this ongoing motor circuit activity. Dopamine modulates this activity, and in Parkinson's disease, you have a disbalance, which leads then that the indirect way is activated and the direct way gets underactivated. The result, finally, is a decreased stimulation of the cortex, which then translates in the clinical signs of slowing of movements, reduced amplitudes, which characterize Parkinson's disease. Now, first, to start what TMS can do, probably most of you are familiar with what we call motor evoked potentials, where we apply this impulse on the motor cortex, elicit action potential that excites the motor neuron in the motor cortex, leads to an descending action potential, which elicits then discharge of the second motor neuron and leads then to a muscle contraction. So we can evoke a so-called motor evoked potential. We have different parameters that we can measure. We can measure the time, the latency of the conduction, which indirectly reflects the integrity of the corticospinal tract. In Parkinson's disease, this exam is normal, which speaks for the integrity of the motor cortex. Speaking about